back to the deep dive. Today, we're jumping into something truly mind-bending. You sent us an incredible stack of sources on one of the biggest, most ambitious projects in all of science.
We're talking about the century-long quest to build a quantum theory of gravity.
Exactly. For decades, physics has been living with this deep crisis, a fundamental conflict between its two greatest achievements. So today, we're plunging headfirst into what many consider the most mathematically rigorous attempt to solve it. Loop quantum gravity.
It really is the ultimate challenge. On one hand, you have general relativity, Einstein's theory. It's beautiful. It describes the universe on the grand scale, planets, galaxies, the expansion of space-time itself as this smooth, continuous fabric.
And it works perfectly. Spectacularly well on those large scales.
Absolutely. But then you have the other pillar, quantum field theory. This is the language of the very, very small. It governs all the other forces, all the particles in the standard model.
And it's also breathtakingly successful. The precision is just phenomenal. But the problem starts when you try to make them work together.
And that's where you hit the wall. You get what your sources call the crisis of quantum gravity. The moment you try to apply the standard tools of quantum mechanics to gravity, the whole thing it falls apart.
It fails spectacularly. My understanding is that it boils down to a problem with infinities, right? When you zoom in and try to calculate things at really short distances, the mass just explodes.
That's a perfect way to put it. Specifically, in quantum field theory, you calculate forces using these things called loop diagrams, which represent virtual particles popping in and out of existence. For the other forces, we have a clever mathematical trick called renormalization to handle the infinities that pop up.
You sort of sweep them under the rug by bundling them into things you can measure, like an electron's mass or charge.
You do, and it works beautifully. But with gravity, it's a different beast. The infinities are relentless. They're more complex. They appear everywhere, and you'd need an infinite number of parameters to absorb them. It's what we call non-renormalizable. The math just breaks.
So the message is loud and clear. The toolkit that built modern particle physics is fundamentally, structurally, the wrong tool for gravity. You need a completely new idea, a paradigm shift.
Precisely. You have to go beyond that perturbative approach entirely. And that right there is the entry point for loop quantum gravity, or LQG. It's not just another theory, it's a whole new methodology for how you even start to quantize gravity.
And our mission for this deep dive is to get to the bottom of how it does that. It takes a path that its main rival, string theory, initially shied away from. It's this radical idea of background independence.
And that one philosophical choice changes absolutely everything. You see, string theory generally starts from a different place. It's aiming for a theory of everything.
A TOE, right. Unifying all the forces at once.
Exactly. And to do that, it traditionally has to assume a pre-existing stage for its actors to perform on. It assumes a fixed classical background, usually a flat spacetime, and then it puts its quantum strings on top of that.
So in a way, it's committing a little bit of a classical cheat. It's saying, let's assume space-time exists, and then let's do our quantum physics.
It's background dependent. The stage and the actors are separate. LQG says, no, that violates the most profound lesson of general relativity. Einstein taught us that gravity is the geometry of space-time. They are one and the same thing.
You can't separate them. The gravitational field literally is the metric that defines distances and times.
And if you're going to quantize the gravitational field, you have no choice but to quantize the metric itself. You have to quantize geometry. And that process must be, from the ground up, background independent.
Which means the theory can't start by assuming space-time is already there.
It cannot. And that leads to the first really profound aha moment for you, the listener. If space and time aren't fundamental inputs to your theory, if they are defined by the gravitational field you're quantizing, then space and time themselves must emerge from the quantum theory.
That's a massive shift in thinking. So if space and time are emergent, what does that imply about the reality that lies underneath?
It forces it to be discrete. The smooth, continuous world of Einstein has to be just a large-scale approximation of something granular, something atomic. At the deepest level, space and time must be built from indivisible quantum building blocks. And the rest of our deep dive is about figuring out what those blocks are and how they build our reality.
Okay, so let's unpack that. It's a monumental task. If you're throwing out the background, the very stage of reality, where do you even begin to build a quantum theory of geometry?
Well, the first step is a standard procedure in physics called canonical quantization. It's the mathematical recipe for going from a classical theory to a quantum one.
It's sort of like how you go from knowing a planet's exact position and momentum to describing an electron with a fuzzy probability wave, a wave function.
That's a great analogy. You take your classical variables, in this case the metric tensor that describes geometry, and you try to turn them into quantum operators that act on a state space. The problem was, when you did this with the standard variables from general relativity, the equations became a nightmare.
Just mathematically intractable.
Utterly. The central equation, called the Wheeler-DeWitt equation, was so horrifically complicated that it blocked progress for decades. The entire canonical approach seemed like a dead end.
So the first big move wasn't solving the equation, but finding a better way to write it down. New language. And this brings us to a huge breakthrough in 1986, the Ashtekar variables.
This was the game changer. It was a complete reformulation of classical general relativity that used a new set of variables that were much, much friendlier to the process of quantization. Instead of the metric, the theory is described by two new things: the Ashtekar connection, called ADEL, and something called the densitized electric field, ADEL.
Okay, let's break those down. What is a connection? What information is it carrying?
The connection, ADEL, is the really crucial insight. Mathematically, it's a gauge field. This was the key simplification, because it makes gravity look, mathematically, a lot like the other forces in the standard model, the strong and weak nuclear forces.
The forces we already know how to describe with quantum field theory.
Exactly. A connection basically tells you how to parallel transport a vector. Imagine you're walking on a sphere with an arrow. A connection is the rule that tells you how to keep that arrow pointing in the same direction as you move. In gravity, that rule is dictated by the curvature of spacetime. So ADEL encodes all the information about curvature.
So you're recasting gravity, which is about geometry, into the language of gauge theory, which is about forces, even though it's still fundamentally geometry.
That is the genius of it. And its partner variable, the electric field dollars, is what's called a densitized triad. You can think of it as defining the actual physical geometry of space at each point, the local sense of distance and volume.
And together, Enel and dollars are what physicists call canonically conjugate.
Yeah.
Like position and momentum. They're a perfect pair for quantization.
A perfect pair. And when you rewrite the horrifying constraint equations of GR using these new variables, they become, well, not simple, but dramatically simpler, especially the Hamiltonian constraint, the one that governs the system's evolution. It went from a messy differential equation to a simple polynomial and algebraic equation.
That seems like a purely mathematical trick, but it unlocked everything.
It was the necessary precondition. It made the problem look like something we knew how to solve. It put gravity in the same ballpark as non-abelian gauge theories, which we have a whole toolbox for.
Okay, so you have the right variables. Now you need to figure out what you can actually measure in the quantum theory. What are the observables? And this is where the loop quantum gravity comes from, right?
It is. Instead of trying to define the quantum field at every single point in space, which is what leads to those infinities we talked about, you define observables that are spread out, that are non-local. The most fundamental of these is based on the holonomy of the connection, holonomy.
Holonomy. That's what you get when you parallel transport a vector all the way around a closed loop and see how much it is twisted or rotated when it gets back to the start.
Precisely. The amount of that twist is a measure of the curvature, the gravity contained within that loop. So you define an observable, a Wilson loop, as the trace of that holonomy. It's a number that captures a piece of the gravitational field's geometry.
It feels very geometric, very intuitive.
Yeah.
But why build the entire theory out of these loops? Was it just a good guess?
Not at all. There was a stunning piece of mathematical justification for it. An independent discovery by Ted Jacobson and Lee Smolin. They were working on the old, unsolved Wheeler-DeWitt equation.
The super complicated one.
That's the one. And they found that if you took these Wilson loops, these traces of holonomies around smooth, non-intersecting loops, they were a class of simple, exact solutions to that equation.
Whoa, so the central unsolved equation of quantum gravity was basically screaming that its natural language was loops.
It was. It was a mathematical signpost pointing in exactly this direction. It meant that the fundamental quantum states of gravity had to be built out of these one-dimensional lines and loops. That discovery validated the entire approach and set the stage for defining the structure of space itself as a kind of polymer, a network of these fundamental threads.
So we have the new variables, R-nuller, that made the math manageable. And we know from the Wheeler-DeWitt equation that the quantum states should be built from loops. So to take that next step, what happens when you use these loops to actually construct the quantum states of space? This is where we get to spin networks.
That's right. The simple, non-intersecting loops were the first step. But a realistic quantum space needs to be more complex. You need to allow loops to cross and interact. And when you generalize the mathematics to handle intersecting Wilson loops, the structure that naturally emerges is the spin network.
And this is an idea that was actually around before Loop Quantum Gravity, wasn't it? From Roger Penrose.
It was. It's a fantastic piece of history. Penrose came up with spin networks back in the 1970s. For him, it was a totally abstract, combinatorial idea to try and build space from just the rules of angular momentum with no reference to gravity at all.
And decades later, this abstract idea finds its perfect physical home as the fundamental description of quantum space in LQG. So describe one for us. What is a spin network mathematically, and what does it represent physically?
Okay, so mathematically, a spin network is a graph think nodes connected by lines that's embedded in our 3D space. And this graph is colored with labels. The links, or the edges of the graph, are labeled by numbers called spins.
Like the spin of an electron.
Very much like that.
Yeah.
They are integers or half integers, and they correspond to representations of a symmetry group called spacetime, which is the group of rotations in the internal space of the theory. You can think of each label, each spin, day dollars, as a quantum number telling you something fundamental about that link.
And what about the other part, the nodes where the links meet?
The vertices, or nodes, are also labeled. They're labeled by things called intertwiners. The job of the intertwiner is basically to be a traffic cop. It tells you how the spins flowing in on the links are routed and combined at the node, and it ensures the whole structure is physically consistent, what we call gauge invariant.
So every labeled graph, every specific combination of links, nodes, spins, and intertwiners is what exactly?
It is a single, specific, unique quantum state of the gravitational field. It's a snapshot of what a piece of quantum space is. The set of all possible spin networks forms a basis for the state space of the theory.
And importantly, this set of states, after you account for duplicates, is countable. It's discrete. You can list them. 1, 2, 3.
It is. And that discreteness is not an assumption, it's a result. And it leads directly to the theory's most powerful and profound kinematic result, which was proven by Carlo Rovelli and Lee Smolin in 1994.
This is the big one.
This is the big one. They constructed the quantum operators for physical area and physical volume, and they proved rigorously that these operators have a discrete spectrum.
Meaning that area and volume are not continuous. They can't take on just any value. They come in discrete steps, like the energy levels of an electron in an atom. Space is literally atomic.
It is the ultimate consequence of being background independent. Space is not infinitely divisible. There is a smallest possible non-zero area, a smallest possible non-zero volume. Any attempt to measure a geometry smaller than that just gives you zero. That fundamental scale is the Planck length, about 1035 meters.
And suddenly the abstract parts of the graph get a physical meaning. The links and nodes aren't just lines on a page anymore.
Not at all. A link in the network, labeled by a spin J-integral, represents a fundamental quantum of area. If a surface in space is pierced by that link, it contributes a specific chunk of area to that surface. And the nodes, the vertices, represent fundamental quanta of volume. Each node is an indivisible atom of volume.
This is so elegant. The whole problem we started with, the infinities that plague quantum gravity, this just solves it from the ground up.
It's not so much a solution as it is a dissolution of the problem. This inherent discreteness acts as a fundamental, built-in ultraviolet regulator. The very reason you get infinities in the old approach is because you integrate over smaller and smaller, arbitrarily tiny distances.
But if there's a smallest possible distance, you can't do that anymore. The integration has a physical cutoff.
The theory doesn't let you. It says there's no such thing as a distance smaller than the Planck length. So those catastrophic, non-renormalizable infinities are just. They're precluded from ever appearing. The theory is finite because the geometry it describes is finite and discrete at its core.
So it doesn't just fix the infinities, it redefines reality in a way that they can't even exist.
It's a radical and I think a very beautiful redefinition. The mathematical rigor of the theory is guaranteed by its very structure.
Okay, but this brings us to the biggest question for you, the listener. If space is fundamentally this clumpy, granular, atomic network, why does the world around us look so perfectly smooth? My desk, the air, the entire universe looks continuous. How do you bridge that gap?
That is the crucial question, and the bridge is a concept called weave states. This is the mechanism for recovering the smooth, classical world of general relativity at large scales.
So what is a weave state?
A weave state is an incredibly complex quantum state. It's not just one spin network, it's a superposition of a huge number of them, all woven together in a very specific way, designed to approximate a smooth, classical geometry like flat space, when you look at it from far away.
I love the analogy of a piece of fabric. From a distance, a t-shirt looks like a smooth, continuous 2D surface. But if you get a magnifying glass, you see the individual threads woven together.
That's a perfect analogy. The weave state is the formal version of that. It's the rigorous mathematical implementation of John Wheeler's old idea of space-time foam to make a region of space look smooth to us. The threads, the links of the spin network, have to be incredibly dense, packing in about 1 link per Planck area.
That sounds computationally impossible.
It's a huge challenge. Constructing these states and proving that they actually do what they're supposed to do, that they approximate a given classical metric, is one of the major technical hurdles. These weave states are our candidates for the world we see, and proving that the theory reliably produces them and that they behave like GR is the most critical test of the theory's connection to reality.
Okay, so we've built a static picture, the kinematics. We have these 3D snapshots of quantum space called spin networks. But the universe evolves, it changes. So now we have to talk about dynamics. How do we get from a 3D picture to a 4D space-time?
And this is where we run straight into one of the deepest, most difficult conceptual problems in all of physics. The problem of time.
Right. In all other physics, time is just there.
Yeah.
It's the background parameter that everything evolves against. But in general relativity, time is part of the space-time fabric that is the gravitational field.
Exactly. So if you quantize the gravitational field, you are necessarily quantizing time itself. Time is no longer a fixed external clock. It becomes a quantum operator. And because of a deep symmetry in GR called diffeomorphism invariance, the equations of the canonical theory, the Hamiltonian constraint, actually force the total energy of any physical state to be zero.
Which basically means the state doesn't evolve in time. The universe in this picture is frozen.
The fundamental equations are not evolution equations, they're constraint equations. Time, in a sense, just disappears from the canonical formulation. It's a huge conceptual hurdle.
So if the Hamiltonian doesn't just push the system forward in time, how do we describe change at all? How does one spin network turn into another?
To answer that, we have to shift our perspective. We move from the canonical picture of static states to a covariant path integral approach, an idea pioneered by Richard Feynman. And this leads us to the theory of spin foams.
So instead of a frozen state, we look at the history of the state, the process.
Precisely. You ask a different question. You ask, what is the probability amplitude for the universe to transition from this initial 3D geometry, represented by one spin network, to this final 3D geometry, represented by another? The spin foam is the calculation of that transition.
So if a spin network is a 3D slice of quantum space, the spin foam is the 4D history of that space as it evolves from one slice to the next.
That's it exactly. A spin foam is the sum over all possible 4D histories that connect the initial and final spin networks. Mathematically, it's a structure called a 2 complex. It's built out of 2D faces, which are bounded by 1D edges, which meet at 0D vertices.
Let's make that concrete. What do those parts, the faces, edges, and vertices, represent in this atomic picture of spacetime?
Okay, so if you think about the 3D spin network evolving through time, the nodes, which were quanta of volume, trace outlines in 4D. Those are the edges of the spin foam. The links, which were quanta of area, trace out surfaces in 4D. Those are the faces of the spin foam.
And what about the vertices, where things happen?
The vertices of the spin foam are the most important part. They are the fundamental interaction events. A vertex is a point in 4D spacetime where the structure of the graph changes, where one spin network configuration transforms into another. It's a quantum leap of geometry.
It really is like a tapestry being woven in 4 dimensions. The sources call it a granular celestial tapestry.
That's a good picture to have in mind. And every 2D face in that tapestry is labeled by a spin, just like the links were, which tells you its area. The whole history is built from these quantized geometric pieces.
But how do we know this spin foam idea isn't just a completely separate theory? How does this covariant historical picture connect back to the original canonical theory with its frozen states and constraints?
The connection is beautiful and deep. It comes from the Hamiltonian constraint operator itself. Remember, that's the operator that seemed to freeze everything. Well, it turns out that when you apply that Hamiltonian operator to a vertex in a spin network, its mathematical action is to generate the structure of a spin foam vertex.
So the thing that defines the static state also defines the rules for its evolution.
It defines the amplitude, the probability weighting for a specific quantum interaction to occur. The two pictures, the canonical constraints and the covariant histories, are just two sides of the same coin. The dynamics flow directly from the kinematics.
So a lot of the modern research is about finding the right rules for those vertices, the right amplitudes.
That's been the focus for years. Developing specific models like the EPRL model or the FK model, which are precise mathematical rules for calculating the vertex amplitude. The goal is to ensure that when you sum over all these possible spin foam histories, you get general relativity back in the classical limit.
And a major milestone here was proving these calculations don't just blow up to infinity again.
Absolutely. A critical result, proven in 2011, was that the transition amplitudes in these modern models are finite. Just like the kinematics gave us finite area and volume, the dynamics gives us finite probabilities. The theory is internally consistent and mathematically well-behaved from top to bottom.
It really reinforces this idea that space-time isn't a background. It's a dynamic, emergent, and crucially finite quantum process.
That's the core message. The challenge now is actually doing that sum over histories for anything more than a few dozen atoms of space-time. It's computationally immense.
Okay, a theory can be mathematically beautiful, but to be physics, it has to connect to the real world. It has to solve problems. So let's shift gears to the most exciting part, where this abstract framework has been applied to actual physical systems.
And the most mature, and I think most successful application by far, is in cosmology. This is the field of Loop Quantum Cosmology, or LQC.
So this is taking the full complex theory of spin networks and applying it to a simplified situation, the universe as a whole, which is on average the same everywhere, homogeneous and isotropic.
Exactly. You apply the fundamental rules of LQG, the quantization of geometry, to that highly symmetric setting. And when you do, you get the theory's crowning achievement, the resolution of the Big Bang singularity.
Which is so important because that singularity is the point where general relativity just gives up. It predicts a point of infinite density, infinite curvature, where the laws of physics break down.
They cease to exist. Classical GR cannot say what happened at the Big Bang or what might have come before. It's a boundary to our knowledge.
So how does LQC, with its atomic space, fix that infinity?
The fix comes directly from the discreteness we talked about. There is a minimum possible volume. So in the LQC model, as you run the clock backward and the universe contracts, the density and curvature increase and the gravitational field gets stronger and stronger.
So you can't go to infinity.
It can't. As the density of the universe approaches the Planck density, an unimaginably high number, the quantum nature of geometry becomes dominant. A powerful, repulsive quantum geometric force emerges. It's an effect that simply doesn't exist in the classical theory.
Well, it's like space itself has a maximum possible compression, and it pushes back.
It pushes back hard. This quantum pressure halts the collapse entirely. Instead of crushing down to a point of infinite density, the universe hits this maximum density boundary and rebounds.
It bounces. The big bounce.
The big bounce. The singularity is gone, replaced by a smooth, albeit incredibly rapid, transition from a previous contracting phase into our current expanding one. The universe never reaches zero volume.
That's just a spectacular result. You're not just fixing an infinity, you're replacing a breakdown of physics with a new physical process. What makes physicists so confident in this prediction?
The sources all point to its robustness. This result, the bounce, doesn't depend on a lot of the little technical choices and ambiguities that you often have to worry about in quantum theories. It seems to be a generic, fundamental consequence of applying the core mechanism of LQG to cosmology.
So it's not a fragile result.
Yeah.
It suggests that resolving singularities is just what this theory does.
That's the hope. And it provides really strong internal validation for the whole framework.
Okay, so if it resolves the cosmological singularity, what about the other great singularity of GR, the one inside a black hole?
The same principles apply there as well. First, LQG offers a way to understand black hole thermodynamics from the ground up. The entropy of a black hole is proportional to its area, but why? What is the entropy counting?
In LQG, it's counting the fundamental atoms of area, the number of ways the spin network links can pierce the event horizon to give it that specific total area.
Precisely. You can do a statistical mechanics calculation by counting these discrete geometric microstates, and you derive the Bekenstein-Hawking entropy formula. It's a beautiful connection between microscopic quantum geometry and the macroscopic thermodynamics of a black hole.
And what about the singularity at the center? Does that also bounce?
The theory predicts a similar resolution. As matter collapses inside the event horizon, it keeps getting denser and denser until, once again, it hits the Planck density at the core. At that point, the same kind of repulsive quantum force that drives the big bounce takes over. The singularity is avoided.
And it's replaced by what?
It's replaced by an ultra-dense, non-singular object that some people have called a Planck star.
And does that Planck star just sit there forever?
Well, the prediction is that over very, very long timescales, it can undergo a quantum tunneling process. It bounces, and the black hole eventually explodes as a white hole, the time-reversed version of a black hole, which spews matter out instead of sucking it in.
So a black hole isn't a permanent information prison. It's more like a very, very long-term storage and release mechanism.
That's the idea. And these things, the big bounds, the potential for exploding black holes, are amazing because they're not just theoretical curiosities. They give us distinct, potentially observable signatures to look for in the cosmos.
Before we get to that, we have to talk about matter. We've been focused on quantizing gravity, the stage, but what about the actors, the particles of the standard model? How do they fit into this picture?
That is one of the biggest ongoing areas of research, and it's a huge technical challenge. You can't just take your standard quantum field theory of matter and drop it on top of a spin network.
Because that would be background dependent. You'd be assuming the spin network is a fixed background.
Exactly. You have to redefine the matter fields themselves in a background-independent, loopy way. So an electron field, or a photon field, would have to be described in terms of quantum excitations living on the links and nodes of the spin network.
So you have to quantize matter and gravity together in the same language.
You have to. There's been a lot of progress. We know how to put fermionic fields and other gauged fields on these networks. But getting the full standard model coupled to the full dynamics of quantum gravity in a consistent way, that's still a major work in progress. It's the key step to making this a complete theory of nature, not just a theory of quantum space.
All right, this brings us to the ultimate test, the absolute crux of validation. You have this beautiful, discrete quantum theory. It's mathematically rigorous. It seems to cure singularities. But if it can't show that it actually turns into the general relativity we know and love in our low-energy world, then it's just a mathematical curiosity.
This is the semi-classical limit, and it is the central theoretical problem for the whole field. You have to show that when you have a huge number of these spacetime atoms, a dense weave state, their collective behavior perfectly reproduces the smooth, continuous dynamics of Einstein's equations.
And you have to show that the smooth spacetime itself reliably emerges from that discrete structure. It's a massive computational problem.
It is. And a good place to start talking about this is with the graviton, because its role in LQG is fundamentally different from in string theory.
Right. In string theory, the graviton is fundamental. It's a specific vibration of the string. It's a particle.
Yes. In LQG, there is no fundamental graviton particle. The graviton is an emergent phenomenon. It's a collective excitation, a ripple, on the underlying quantum fabric of the spin network. It's like how a sound wave is an emergent vibration of discrete air molecules. The sound wave isn't fundamental, the molecules are.
So a key test for LQG would be to show that these emergent ripples behave exactly like gravitons are supposed to.
Precisely. And the biggest breakthrough on this front came from the spin foam side of the theory. The critical test was to calculate what's called the graviton propagator.
Which is what exactly?
The propagator is a mathematical function that tells you the probability for two particles to interact by exchanging a quantum of force, in this case, a graviton. Getting the propagator right is the first and most essential step to proving your theory has the correct classical limit. It's how you recover Newton's law of gravity, for example.
Did they do?
They did. Using the modern spin foam models, specifically the EPRL vertex, researchers were able to calculate the two-point correlation function for the gravitational field at large distances. And they showed rigorously that it reproduces the correct graviton propagator of classical GR.
That's a huge deal. That's the first concrete proof that this discrete, background-independent structure can actually produce the classical gravity we observe.
It's the justification for the incredible claim that you can calculate Newton's law starting from a world with no space and no time. It's a major piece of evidence that the theory is on the right track.
Okay, so if the theory is on the right track, it has to be testable. We should be able to look out at the universe and see some tiny signature of this underlying granularity. What should we be looking for?
The main idea is that if space-time is a discrete network at the Planck scale, then very high-energy particles traveling over vast cosmic distances should interact with it subtly. It should act almost like a refractive medium.
Kind of quantum friction or something.
You could think of it that way. The two key effects we look for are modified dispersion relations, or MDRs, and potential violations of Lorentz symmetry, or LSV.
Lorentz symmetry is the bedrock of relativity, the idea that the speed of light is constant for everyone. How would this violate it?
Well, if space has a fundamental minimum length, the Planck length, that might act as a kind of preferred reference frame at that tiny scale. This could cause the speed of light in a vacuum to be very slightly dependent on its energy. A super high energy gamma ray photon might travel just a tiny bit slower or faster than a low energy radio wave photon.
An effect that would be completely negligible normally, but if they travel for billions of light years from a distant galaxy,
that tiny difference could add up to a measurable arrival time delay. So we use things like gamma ray bursts, these huge cosmic explosions, as our laboratories. We look for a time lag between the high energy and low energy photons.
we're using the universe as a giant particle accelerator.
We are. Another potential signature is related. It's called gamma ray threshold anomalies. Basically, very high energy photons can be destroyed when they hit low energy background light in space by creating an electron-positron pair. There's a minimum energy threshold for this to happen.
But if the dispersion relations are modified,
That threshold could shift. LQG models predict this could make it harder for the highest energy photons to be destroyed. So you might see more of them from distant sources than you'd expect. Finding that kind of anomaly would be a direct probe of the graininess of space-time.
that would be a Nobel Prize, no question. Now let's go back to the big bounce. Does it leave a smoking gun we can see today?
It absolutely should. The extreme physics of the bounce happening right before the period of inflation should have left a specific imprint on the primordial fluctuations that got stretched across the sky and became the cosmic microwave background, the CMB.
The baby picture of the universe.
Exactly. But this is where we hit a major empirical challenge. There was a big study in May 2023 that took real data from the Planck satellite and compared it to simulations based on a simple LQC bounce model.
And what did they find?
They didn't find the specific signature that simplified model predicted.
So, does that kill the theory?
No, not at all. The sources are very clear on this. What it kills is that specific, overly simplified model. It tells us that the reality of the pre-inflationary universe was more complex. To match the incredibly precise Planck data, the LQC models need to be much more sophisticated. They need to include more detailed physics about how perturbations behave during the bounce.
So it's not a failure of the theory, but a sign that the models connecting it to observation need a lot more work. The bridge isn't finished yet.
That's the perfect way to put it. The core prediction is robust, but building that detailed bridge from the quantum bounce to the CMB we see today is the next big frontier.
So to wrap up this deep dive, let's pull the lens back and look at the whole landscape. We've seen LQG defined by its rigorous, background-independent approach, where geometry is quantized and the graviton is an emergent idea.
And it's useful to contrast that one last time with string theory. String theory starts theoretically, it was initially background dependent, and its fundamental entity is the string, with the graviton as one of its fundamental vibrations.
They have very different strengths, right? The big appeal of string theory has always been its potential for unification.
That's its crown jewel. It naturally includes all the forces and matter in one package. It has a built-in framework for everything, which LQG has to work very hard to add in later. The challenges for string theory are different, the extra dimensions, the huge landscape of possible solutions.
And LQG's strength is its opposite. It's purity and conservatism in a way. It sticks laser focused to the principles of general relativity.
It does. Its strength is its mathematical rigor, its direct quantization of GR, and the way discreteness is a consequence, not an assumption, which automatically solves the ultraviolet infinity problem. And its biggest concrete success is resolving singularities in cosmology.
But as we've seen, it's not a finished theory. Let's lay out the biggest open challenges, the things that need to be solved for it to be considered complete.
Okay, challenge number one is really about finishing the foundations. Completion of dynamics. We have the canonical picture with spin networks and the covariant picture with spin foams. We have strong evidence they're related, but we need a complete, rigorous proof that they are fully equivalent and consistent. That's a major mathematical project.
Challenge number two is the one we keep coming back to, the classical world.
The full semi-classical limit. This is the big one. We've shown it works for the graviton propagator in a simple case. But we need to prove that full-blown general relativity emerges from the theory for any generic spacetime, not just simple ones. This means figuring out how to do these incredibly complex spin foam calculations for huge systems.
And the final challenge is the one that really matters for physics. Can we prove it's right?
Experimental verification. It's the bottom line. We have these tantalizing predictions, these Lorentz symmetry violations, the CMB signatures from the big bounce. but the effects are incredibly tiny. We need our telescopes and detectors to reach unprecedented sensitivity. And on the theory side, as we saw with the CMB, we need to build much more refined models to know exactly what signature to look for.
It's an amazing journey. We started with this crisis of infinities, and the solution forced a complete reimagining of reality. We went through new variables, discovered that space itself is atomic with spin networks, figured out how it evolves with spin foams, and ended up curing the biggest diseases of classical physics, the singularities.
It really is a theory at a crossroads. The foundational kinematics are solid, the mathematical structure is beautiful and finite. Now it stands at this crucial threshold where it has to prove its connection to the macroscopic world and hopefully find that one definitive signature out there in the cosmos.
So what does this all mean for you, the listener? We've learned that in loop quantum gravity, space is not some static, empty background. It's a dynamic, evolving atomic substance. So here's the thought I want to leave you with. If space and time are truly just emergent properties of this interacting quantum network, if the smooth, continuous reality we all experience is just a low-energy illusion, an approximation of a fundamentally digital granular structure, what does that imply about the nature of all classical reality? If the very stage is quantized, is it possible that every continuous thing we see is just a coarse-grained average of some deeper, discrete, and ultimately computational reality? That's something for you to mull over as you continue your own deep dive.